Hello, everybody. I'm very happy to be here. It's a very nice city, very nice building, and I'm happy to be able to present you an algorithm which I have been developing for more than 3 years, together with my advisors. An algorithm which was designed to be able to learn from its own errors in order to get better and better. We call it Predator. I'm a computer vision researcher, and my goal is to enable machines to see. What I mean by that, we typically take a video camera which is giving us some video stream, and every day I'm trying to write an algorithm which is trying to extract some useful information from the video. And the useful information is, for example, understanding motion. We are living in motion, and we want to understand how things move. For example, in this video, my goal is to understand how the motorbike moves. I would like to draw basically a bounding box, a dot around the motorbike as it moves. For a human, this is very easy. We can do it without even thinking about it. You can always point your finger at the motorbike. So we don't think it's difficult, but for a machine, it's a very difficult task. And people try to do it for ages, because this task is at the core of a number of applications. If you want to navigate a robot, you need to know how objects move. If you want to interact with a computer, you need to understand how humans move. If you want to have some augmented reality application, you need to know how a surface is changing its pose. So there has been a lot of research, and there are already algorithms which are doing this kind of functionality, but they are usually very specific. And what is more interesting, when you run these algorithms, they don't change their performance. They will be always the same, and you cannot apply them to anything what you want. So what I wanted is to build an algorithm which is basically learning itself, which is getting better and better over time, and which you can take and apply it to any object you want. So this is example what I have done. The input to the algorithm is a single bounding box like this. After that, the algorithm tracks the motion of the fingers or anything what you selected and remembers what the object looks like and what is not an object. So we are online building a model representation of the object which we have selected. And this allows us to be very, very robust because we remember this model and we can use it to detect the object anywhere in the image. So we have somehow managed to combine tracking, detection, and learning into a single algorithm which is running in real time. And there has been, therefore, quite a lot of attention because people started realizing that we can apply it to different problems. The same algorithm can be applied to different problems. So today, I would like to just show you the way how I came to the algorithm, the story behind, the thinking which led me to develop it. So it all started when I was doing master thesis in Prague, and I was studying control theory. Control theory is a field which is trying to control machines. You have a helicopter or a car, and you want to build an algorithm which is able to control the machine in order to do what you want. Helicopter should fly. And we are studying this on very simple examples, simplified problems, such as this ball and beam. So in this case, the goal is to control the machine in the way that the ball is always in the center here. And you can see that if you push the ball away, the algorithm is reacting on it. Like a human, you want to balance the ball on the beam. Another example, if you just make it in 2 dimensions, you can throw a ball on a plate, and the algorithm is again trying to balance it and get it into the middle. So in these examples, I first saw that you can really make algorithms which look alive, which are intelligent. And I really like this way how you can interact with it, because it was really cool. And what we learned during the classes is that you need to have something special in order to realize this. You need to have feedback. Feedback is quite old concept introduced by Norbert Wiener in his book Cybernetics. And the idea is following. You first define what you want to achieve. So you have a goal. Once you have the goal, you are able to measure error. You are able to measure how well you are performing. And using this error, you are able to react and control the system. So these 3 steps are essential to make these systems work, and they are essential in order to make planes fly. So how to realize the feedback, and how computer vision came to the picture. So imagine that you have the ball and the plate, and you put the camera at the top. So the camera sees a picture like this one, very simple picture where you know where you want to be, and you have a picture of the ball. So you apply some computer vision technique to detect the ball, and you are able to measure the error. And now you have the error, and you can compensate, you can control the system. And basically, this detection was essential to realize the feedback. So we were studying how we can detect the ball, and this is basically why we started learning about computer vision. And we started doing more complicated things, such as detection of faces. Detection of faces is very similar to detection of the ball, but it's more difficult problem because the face appearance is much more versatile. And you can, nowadays, face detection is basically anywhere, any camera which you have has face detection built in. So how does it work? Well, the idea behind face detection is pretty simple. It's called scanning window. You start in top left corner, and you detect or you decide if there is a face or not. Then you slide the window to the right, and you do the same thing, and you slide the whole image like this. You do it for different scales, and eventually you are able to find the face. So this scanning window is at the core of face detection. And in order to do it, you need to know what you are looking for. You need to know a model of the face. So just to make a comparison, when you are looking for a dot, it's easy. You can describe it by a color. If you are looking for a face can look very differently in different illumination, expressions, and so on. And there are literally millions of parameters which you need to know. And you cannot just type them into your program. So for this reason, you are using something like training examples. You collect positive examples, all appearances, how face looks like. You collect negative examples, everything what is not a face, and then you run it through an algorithm which can take days or weeks, and you end up with a model which describes the face. So you use machine to learn how the face looks like. So once you have this, you can apply it to different problems, and we have done it. We have done it for different faces, for different poses. We have done it for faces in a car or recognition of license plates, maybe recognition of the logo of the car. And you can always use this same trick. You collect examples, train classifier, and you have your algorithm. But what I didn't like about this approach is that you really need a lot of time for training. You need days or weeks to train the system. And I wanted something what was faster. I wanted something what you can play with and what you can do in real time. So essentially, I wanted to move from this approach of offline learning with millions of examples and days of training. I wanted to move to something what is called online learning, something what is faster, where you have just a single example given by bounding box, and you want to be in real time. So I have been trying this for some time, and this is one example when you can see one of the many failures where it didn't work. You can see that I wanted to track the 3 fingers here, but the algorithm failed pretty quickly. Here is another example where I was trying to focus on interesting parts of the object. So these dots represent something what is interesting, and you can see that when the car goes behind the trees, the algorithm fails as well. So I have done a lot of failures there, and it seemed that I want maybe too much from the algorithm. But then I realized that maybe I just need to change the way how I think about the problem, the change of philosophy. So far, I was considering error as something bad, something what should be avoided. And therefore, we were collecting these huge amounts of training examples, and we tried to avoid error. But as a human, we know that we cannot avoid errors. Instead, we should try to learn from errors. So I wanted to make this kind of approach to the program as well. So we accepted that we will make error, and we decided to learn from these errors. So I basically came to the idea from control theory when the error was used to control the system, and the error was the driving force. So now the question was how we can introduce the error into the algorithm, how the predator can recognize that it made error. And the idea is simple. In real world, objects move on trajectory in space. When I move on the stage, I basically define a trajectory in space. And some camera is observing this space, and we are using this scanning window. So you can imagine that we are basically discretizing the whole space into all these dots. And in this space, my location is basically described by this kind of trajectory. So we know what we want to achieve. We know that our algorithm should generate a trajectory in space. And this was information which is obvious now, but people didn't use it at all. So once we know what we have the goal, we can recognize what is wrong. We know that if the algorithm generates something like this, random dots in this space, we know that this is not correct, and we can recognize this error. So that was simple then. We know what is an error. We can just remember the error, and these are the examples. These are basically the errors which we identified. These are also errors which we identified. So every error we found, we remember it in order to avoid it for the later. So suddenly, when we realized this thing started to work, we formalized the learning theory behind as a dynamical system, and we found the stability conditions. And this really allowed us to train very fast algorithm in real time. Then we had all the three components which we needed. We had the learning component, which is essential for the whole thing. We added it with detection and tracking, which I don't have time to talk about. And we managed to combine them in a very interlinked manner. So all the components are helping each other, and therefore the system is better. So once we have this, we can apply it to all different kinds of videos, such as this motorbike. So in this case, the algorithm was initialized by a single bounding box. There was no other information. And now it's able to follow the object, as you can see here. But at the same time, it's learning how the motorbike looks like and what is not on a motorbike. So you can take this, and maybe you can use it somewhere else, maybe in different camera. You can use it to stabilize a video. If you are on a motorbike, having your camera on the helmet, you can stabilize the motorbike in front of you. You can use it to analyze motion of animals, which is very important for behavior analysis. And there are many people who are interested in this. You can use it to navigate a robot, such as a flying drone. You would like to select a car which is escaping police and maybe automatically have a helicopter which is following it without the need to have a pilot there. And you can use it to annotate movies. You can select a face in the first frame, and then you can track the whole face in the whole movie, and then you can think about some automatic or intelligent fast forward. So you want to just know the scene where the guy is present. So there has been quite a lot of applications, and especially when I showed my video on YouTube, people started sending me a lot of emails with different proposals, different ideas, and this is just a short list of these ideas which I got. So I wanted to do something about it, and I wanted to make this algorithm available for people. So I decided to release it for open source, which is now under GPL license 3. Thank you. I appreciate it.
Okay, sure.
And there are currently more than 1,000 people who are working on this problem. One of the algorithms which I really liked is this navigation of this small robot, which is following target, as you can see here. So what to do next? I have done algorithm which is following one target, but this is not the ultimate goal of computer vision. This is not how we see. We want to do some detection, or we want to follow hundreds of targets, and this is some preliminary results where each of the dots has the property to be tracked, learned, and detected at the same time. And you can see the precision which we achieved here and the robustness at the same time. So this might be interesting for artists who want to make maybe artificial makeup or special movie effects and so on. So I really believe that the idea of Predator can be done really forward, and I am really working on it to make it happen. So right now, I'm on my way to Silicon Valley to find more, and I'm very happy that I was invited here and I was able to tell you my story. Thank you very much.